So hello everyone, welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. So it's my great honor to introduce our distinguished speaker today, Professor Rob Nowak from the University of Wisconsin-Madison. Professor Nowak is a McFarland Bascom Professor in Engineering at the University of Wisconsin-Madison. He is a professor in the Department of Electrical and Computer Engineering, and he is also affiliated with the Departments of Computer Science, Statistics, Biomedical Engineering, and Wisconsin Institute for Discovery, Wisconsin Optimization Research Consortium, and Machine Learning at Wisconsin-Madison. He is also an adjunct professor at TTIC. His research focuses on signal processing, machine learning, optimization, and statistics, where he has made many fundamental contributions. In addition, he is a fellow of IEEE and has received numerous awards, including General Electric Genius of Invention Award, NSF Career Award, the Army Research Office Young Investigator Program Award, the Office of Naval Research Young Investigator Program Award, as well as many Best Paper Awards. Today, Professor Nowak is going to talk about nonparametric active learning with kernels and neural networks. Please join me in welcoming him.
Well, thank you very much for that kind introduction. It's a real pleasure to be here. I want to thank the organizers for putting together this awesome lecture series, and I'm really honored to be a part of it today. And I thank everybody who's tuning in out there. And I'll go through my talk, and then hopefully at the end we can field some questions from the audience. I just wanted to say one thing. Recently, they changed my title to Nosbush Professor in Engineering, so I just wanted to put that in there because that was a kind donation from the Nosbushes, so I wanted to give them a little shout out, and their support has helped me in this research that I'll be presenting today. So what I'm going to talk about is nonparametric active learning with kernels and neural networks, and the basic flow of the talk is going to go like this. First of all, I'll kind of introduce the idea of active learning, motivate it. Then I'm going to go over some of the kind of past work, research, and methods in active learning. And then the second half of the talk will really focus on kernels and neural networks and talk about some very recent work that I've been doing with some of my collaborators. So without further ado, I'll jump in. Is there anything else you guys wanted to add on your end?
No, that's all.
Okay, well, Ben, thanks for putting this together. So, oops, somehow, there we go. I just didn't have my cursor in the right place, I guess. So this picture is just meant to depict the conventional machine learning pipeline. And the basic idea is that we have a huge pool of unlabeled raw data, for example, images. Then we're going to select, usually at random, a subset of those images and ask a human expert to label them for us. And then that labeled data is going to be turned over to a machine learning algorithm that's going to try to build a predictive model based on the labeled examples. And the hope is that that model then predicts the labels of new examples as well as that human expert would do. And so this has been kind of the architecture that's been behind a lot of huge successes that we've heard about in recent years, and I don't need to tell everybody about them, but in classification, NLP, translation, game playing, all these areas. But if you look underneath the hood of some of those methods, there's a lot of data-intensive processing, and often that data-intensive processing or cost involves human effort too. So for example, in learning to classify images, those machines are being trained on data sets consisting of millions of labels of images, and those labels have to come from people. So people had to invest time and effort to develop those data sets. Similar things happen in lots of areas of machine learning. And also, in game playing, the games are being mastered by machines by playing more times and more plays than even my teenage son can stomach. And so something's just kind of a little bit maybe unacceptable here, in that we have to train these machines with so much data. So hopefully this talk will go smoothly. My teenage son, I don't know if he's on the system right now eating up bandwidth, but hopefully I won't have any glitches on my end. All right, so kind of this motivates the question of, can we train machines with less labeled data and less human supervision? And that focus on the human labeling cost is the one that I'm going to really focus on today. So that motivates the idea of active machine learning. And here what we're going to do is we're going to kind of change this pipeline a little bit. So instead of just taking a random subset of unlabeled examples and asking our human expert to label them, we're actually going to give the machine an extra little mechanism, an algorithm that's going to select examples from the pool of unlabeled data and request the human expert to label those. And so the idea is the machine is automatically and adaptively selecting the most informative examples for labeling with the aim of reducing the load or effort required from that human expert. And so what you can roughly think about is, as the machine sort of learns a predictive model, it can use that predictive model and apply it to the unlabeled data, and then on examples in the unlabeled pool that it feels especially uncertain about, those are ones that it will ask the human expert for labels on. So that idea, active learning, it's been around for decades in the machine learning research field, but recently it's really kind of risen to the level of commercial interest. And so these are a couple of examples. Amazon has a tool and service they call SageMaker Ground Truth, and they say that data is only routed to humans if the active learning model cannot confidently label it. Exactly what I was just saying in that last figure and slide. There's another service called Prodigy, which is an annotation tool powered by active learning. So people are really trying to actually develop systems for active learning that can operate at scale and in real commercial applications. So let me give you one motivating example that comes from some work we've done ourselves, and this is in sort of disease prediction from electronic health records. And so the basic idea here is that we have a database of electronic health records. We can ask human experts to label those records, for example, to predict whether somebody has or may develop a disease like cataracts, turn those labeled electronic health records over to our machine learning algorithm, and the machine can try to build a predictive rule. It can also use a partially learned rule, apply it to other unlabeled electronic health records, identify records that it's especially uncertain about, and then request the human experts to label those particular cases that it's having trouble with. And so the motivation here is that these human experts are not just people like you and me. They're experts who are trained to read and interpret electronic health records. So they have special qualifications and training. It takes them several minutes just to look at a single electronic health record, and they're highly paid professionals. So these are very, very expensive labels to collect. And so that's why active learning that minimizes the number of labels we need from these human experts is a really attractive proposition in this application. So here's a picture of how this might go. And what I'm showing you up there in the upper left here is a kind of rendering of a classification learning problem with two electronic health record features. In actuality, the example that I'm going to talk about here has about 6,000 electronic health record features, and we're using linear classifiers on those 6,000 features to try to predict whether somebody has cataracts or not. So up here, what I'm showing you is a bunch of electronic health records. Each dot is an electronic health record. The gray dots are unlabeled records, and the red and blue dots are ones that are labeled. Maybe red means that person has the disease. And so given this set of labeled examples, this would be our best linear classifier, this green line here. And so now the question is, if we want to improve that classification rule, we need more labeled examples. So what would passive learning do? Traditional passive learning would just select one of the unlabeled electronic health records at random from the remaining pool and request a label for it. And as we do this and collect more labels, the test error rate of the learned classifier will improve. And so that's what I'm showing there in the bottom right. Now, what active learning is going to do, remember, the machine is going to try to identify examples that are unlabeled and that it's very uncertain about. And one way to measure uncertainty is to look at examples that are close to its current decision boundary. So for example, this orange one that I've highlighted. And then it's going to request a label for those especially uncertain unlabeled examples. And that will hopefully allow the machine to more quickly learn a very good linear classifier. And the curves I'm showing down there on the test error are actually the actual curves from this real data experiment with 6,000 electronic health record features. And what we see is we get about a 3x reduction in the number of labeled examples required to learn a good linear classifier in this application. And again, those are paid professionals providing these labels, so that 3x improvement is really a consequential sort of factor. It really reduces the cost of training up these machine learning algorithms. So that sounds fantastic, right? We should just be doing active learning all the time. Why wouldn't we? Well, there are some hurdles or challenges that we face here. And so one is just the fact that active learning combines data fitting and data collection. And so it sort of requires this interactive computing and human-computer interfacing that just makes the whole software system a lot more complicated than simply coding up your favorite algorithm in Python. And so because of that, we probably, that's one of the reasons contributing to the fact that people aren't widely using active learning all the time. To sort of address this challenge, we developed an open source software system called Next, which is kind of a system that handles a lot of the interactive database issues and so forth, and essentially allows you just to write your favorite active learning algorithm in Python and then try it out in this testbed platform Next. So that's something that I won't go into more, this sort of system level aspect of active learning, but it's an important one that you need to face.
I'm going to go on a long walk.
Okay, see ya. All right, I'm in the middle of my talk, thanks. Sorry, my son's informing me that he's going on a long bike ride. Perfect timing. Okay, so what's the second hurdle? Here's the second hurdle. Active learning is a closed loop system. It has feedback in it, right? And so algorithm design and analysis is a lot more challenging. If we're too aggressive with this adaptation and feedback, we can actually end up learning a very suboptimal classifier or predictor. So we have to be very careful with that feedback, and that makes analysis and design challenging, as I said. And then third, the data selection in active learning is based on the form of the predictive model. For example, we're using a linear classifier. We use that linear form to guide the selection of which examples to get labels for next. And if that model, that form is wrong, if the reality isn't a linear model, that misspecification or bias can actually be very problematic. And again, it can steer us towards suboptimal solutions. And so this is, kind of a crucial thing to recognize, as George Box, one of the famous data scientists from Madison, famously said, essentially all models are wrong, but some are useful. So I think we have to face reality. Anytime we use a model, it's not really going to be an accurate representation of reality. And so there's going to be misspecification and bias in those models. That's a little less problematic in general passive learning because there's no feedback in it. With this feedback and active learning, that misspecification can be really troubling. And I'll show how that happens in a moment. So those two second challenges, closed loop feedback and model misspecification, are two of the things I'm going to really be focusing on in this talk. Great. So before I get into things, I just want to give people a sense of where active learning helps. And I really want to emphasize that word where, because what I'm going to try to make a distinction of here is the difference between what I call what information and where information. So let me kind of illustrate this dichotomy in a couple of examples. So let's think about probability estimation. I'm just looking at the conditional probability of y given x, and I'm drawing that function over on the right there. So estimating the probability of y given x at each point x, that's a what question. What is that probability? Classification, on the other hand, is a where question. We're really just interested in where is that conditional probability greater than 1/2. And so I'm showing here the sets where the conditional probability is greater than 1/2. Maybe that's where the label should be +1, and on the complement -1. And in classification, that's all we care about, is the identification of those sets, which boils down to the identification of the boundaries of those sets. And those are very localized in space. And so that localization can be exploited through active learning to kind of home in on where those decision boundaries are. Similar things happen. Here's another one, density estimation. What is the density of X? That's a what question. Clustering is more like a where question. Where is that density large? And so again, we're looking at where the density is above a certain threshold, say. And then another example, just to wrap up, is function estimation. What's the conditional expectation of y given x? Well, we don't often need to know the entire conditional expectation function. In bandit optimization problems, for example, all we're interested in is where does that function achieve a max? Okay, so it would be just this point here. And so that's another example of a very localized thing. We're trying to localize the max of a function rather than learning the entire function. So in all these situations, the point here is that active learning can be much more effective and efficient than passive learning for localized where information questions. Okay. Now let me illustrate this in probably the simplest sort of example, and that's learning a one-dimensional classifier. Single threshold classifier. So here what I'm showing you at the top is just a bunch of unlabeled examples in 1D. Here's the entire labeled data set. And then here would be the decision boundary that we want to learn in this case. And what I'm going to show you now is I'm going to try to contrast passive learning, where we just randomly select unlabeled examples and get labels, versus active learning, which sort of adaptively tries to home in on where this decision boundary is. And it's going to do that through a sort of binary search procedure. So that's what I'm showing these two little animations down here. Passive random sampling on the left, active binary search on the right. And what you can see is after just collecting a few labeled examples, the active method has basically nailed where that decision boundary should go, but there's still a lot of uncertainty in the random sampling. And so in this sort of case, it's a really simple little back of the envelope calculation. The error of the passive method goes down like 1 over the number of labeled examples you've collected, whereas the error of the active method is going down exponentially fast in the number of labeled examples that you've collected so far. So there's a huge gain or speed up in how quickly you can learn where that decision boundary is using active learning. So that's super simple. But it turns out this kind of idea and intuition generalizes to very broad classes of problems. And so how do we go to higher dimensional problems? Well, we essentially have a similar notion of binary search, but building upon some of the standard tools in statistical learning theory, like VC theory. And so let me just give you another sort of animation or cartoon to show you how that might work. So we're going to look at a case where we're trying to learn a multidimensional classifier. And we're going to assume that our unlabeled data points are just uniformly distributed in the unit ball, say in d-dimensional space. And we're going to consider linear classifiers that pass through the origin. So here's one of those linear classifiers. But before we get labels, we don't know which one is the right one. So it could be a linear classifier, any orientation in this space. So to begin with, suppose we get a small sample of labeled examples. Okay. We can use these to sort of say, well, what are all the linear classifiers that would consistently classify or correctly classify these few labeled examples? It would be these guys right here. All those linear classifiers perfectly classify the labeled examples that I'm showing you. And so we can sort of think about things this way. We can divide the data space into two pieces. The gray area, where all of those classifiers agree with each other, and then the green area, the green shaded area, that's where one or more of those classifiers will disagree with the majority of the classifiers that remain. And so the idea then of active learning is to say, okay, well, we want to collect some more labeled examples to improve or localize more what the proper classifier should be. So we're just going to collect a random set of unlabeled examples. But instead of asking for labels for all of these, we're only going to request labels for examples that are in that region of disagreement. Because, again, we know they'll all agree on the examples in the gray area. So we only need to ask questions or request labels for examples in the green region of disagreement. We collect those labeled examples, and then we update our region of disagreement. And then we just repeat this process. And by doing that, we can quickly kind of localize where that linear decision boundary should go. So that's disagreement-based active learning. And there's a lot of nice theory that you can build up about that idea. And I'll just kind of summarize it here as follows. If the optimal Bayes classifier, F star, is in a known VC class with some finite dimension D, and we have really nice distributions, for example, bounded label noise, then the difference between the probability of error of our learned classifier F hat and the minimum probability of error, the Bayes error rate, is going to decrease like dimension over number of labeled examples in the passive case. That's the so-called parametric rate. But if we're using active learning, disagreement-based active learning, then the error is going to decay exponentially with the number of labeled examples. So we get a picture like the one I'm showing you down at the bottom there. So we get this huge exponential speed up again, just like we saw with the binary search method in that simple one-dimensional problem. So that kind of summarizes a lot of what we understand theoretically about active learning, or at least most of what the theory says is studying these kind of VC type classes. And so again, you might say, well, fantastic, we get exponential speedups, that's wonderful. Are we done? And the answer is, well, all those impressive gains hinge on a crucial assumption, and that is that the true F star, this Bayes classifier, is in this finite dimensional VC class that we somehow knew which VC class it was as well. And so that's where the problem shows up. That's why we don't see exponential gains usually in practice. It's back to what George Box says. All models are wrong. So we really don't, whatever model class we're using isn't a perfect match to reality. And we need to face that fact and figure out ways to deal with that model mismatch. Okay, so let me just say a little bit about how active learning can break down when models are wrong. So here I'm kind of showing you a simple two-dimensional case. Again, here's our entire labeled data set. And what you can see here is this set of labeled data are not linearly separable. If I use a linear classifier, the one I hope that I learn is this guy right here. That's the best linear classifier. If I force myself to use linear models, that's the best solution I could come up with on these labeled examples. And so active learning may not really perform that much better than passive learning here, because the models don't really match reality. And in fact, it could be even worse. If you're too aggressive in active learning, you might actually end up with a suboptimal solution. And so a lot of the theory really doesn't address this situation of model misspecification in active learning. So we need to think about a new way to handle situations like this. So what's the usual way we would go? Well, maybe we go nonparametric. Since active learning suffers when models are misspecified, maybe we should use nonparametric models that can handle arbitrary learning problems. So this is a natural sort of next step to consider. And there's been a lot of theoretical work on this type of nonparametric active learning problem. I mentioned a few papers there. And so what this work shows is that the theory indicates what the potential of nonparametric active learning is, but broadly speaking, it doesn't really provide practical algorithms for nonparametric active learning. And so that's something that I've been kind of researching for the last few years. I'm going to tell you a little bit about it, beginning with an idea that we had a few years back. And this is sort of a practical approach to nonparametric learning that actually has some nice provable guarantees. And the idea is a sort of generalized binary search on a nearest neighbor graph constructed over the unlabeled data. So first of all, you construct a nearest neighbor graph, and then you use a kind of generalized binary search to try to identify cut sets in that graph that separate clusters of like-labeled examples. So all these examples would be red, blue, and blue. And the kind of theoretical result here is that if the decision boundary, which in this graphical setup is just the cut set of the graph, if that cut set consists of m edges, then we only need order m labeled examples using this generalized binary search procedure to accurately label the entire data set. So that's kind of a nice semi-practical method. We've actually used it on some real practical problems. But it really hinges on this idea of constructing the graph and so forth. So it's not a fully general nonparametric approach. It's really specific to this kind of graphical setup. And so one of the things we've been doing lately is trying to move to other sorts of nonparametric learning models and systems. And this is where my collaborator, Mira Karzan, comes in. She sort of posed the question, can we develop active learning algorithms for popular modern methods like kernel methods and neural networks. And so that's what I'm going to focus the rest of the talk on. Specifically, we're going to look at single hidden layer neural networks and kernel classifiers. These both have the form of this kind of linear transformation followed by scalar nonlinear activations followed by a linear combination at the end to produce the output. So let's kind of get into that. But before I sort of tell you how we approach active learning with these models, I want to tell you about the motivation. And the motivation are these recent insights into what's going on with overparameterized and nonparametric methods in machine learning. And this is this so-called double descent characteristic that has been popularized, especially by Misha Belkin and some of his collaborators. And so what I'm showing you here is the sort of classical textbook story of bias variance trade-offs. And that story says that if you really try to fit the training data, the test error might actually be very poor. You might overfit the data and generalize poorly. So this is a classic bias variance trade-off, and regularization is typically used to try to somehow hit this sweet spot of minimum test error performance. But what people have observed, and now we have some theoretical understanding of, is that if you push beyond this sort of parameter threshold, this is where the number of parameters or effective number of parameters is equal to the number of data. If you over-parameterize and go into the so-called modern interpolating regime, you can actually get models that have zero training error and much better test error performance than you have at sort of this interpolation threshold. And the reason this is happening, the explanation is that we're not just using any over-parameterized or non-parametric model, but we're choosing one that has some maximal smoothness or regularity, which is measured in a certain function norm, subject to these data fitting constraints. And that yields models that generalize well. So the key idea is find a model that fits the data, but find one that has some small norm in an appropriate function space. So here are some experiments also from Belkin and his collaborators showing this double descent characteristic on the MNIST data set. And so here's where we see the classic bias variance trade-off, but if we go to an over-parameterized model, we actually see the generalization error, test error getting better and better. And so the key idea is what's going on in this region, how can it get better? Well, we're not just using any function that fits the data, we're using a function with minimum norm. It has maximal regularity or smoothness, and that's the key idea. So we're going to build on this insight to develop a heuristic for active learning with neural networks and kernels, and then I'll explain more about the justification of that. So here's the idea. We call it interpolating active learners. So what I'm showing you here is a model interpolating 6 labeled data points, the 3 blue points and the 3 red points here, and this is our function that's interpolating those. That could be a kernel interpolator, or it could be a neural network function interpolator. Now we have a lot of unlabeled data that we can ask labels for, and every time we get a label, that will hopefully improve our overall prediction function. And so the question is, which unlabeled example should we collect? We have a choice here. That's what active learning is all about, selecting that next unlabeled example to get a label for. And whichever one we take, the label could turn out to be +1 or -1 in this binary classification setup. And the question is, which example should we label next? So building on the intuition from the double descent idea, what we're going to do is we're going to label the most challenging examples first, those that are going to be the most difficult to interpolate. And I'll explain what I mean and how we identify these examples in a couple of illustrations here. So let's look at this situation. Suppose we decide that we're going to ask for the label of this unlabeled example right here. That unlabeled example sits between these 2 labeled examples that were both labeled red. And if I get a label for U, the unlabeled example, and it turns out to be blue, that's going to be pretty difficult to accommodate because my interpolation function now has to shoot up to interpolate through that point. So while the original interpolator wasn't so crazy, the new blue one has a lot of extra wiggles in it. It's a lot less regular because I have to accommodate this point. So that's a difficult point to interpolate if it turns out to get a blue label. And we can gauge that by looking at the norm of the blue interpolation function. On the other hand, maybe it'll turn out that that unlabeled example will get a red label, right sitting between the two originally red labeled examples. And in that case, it's going to be pretty easy to interpolate. Here's the new interpolation function in red. It's easy to interpolate, and we can again measure that by looking at its norm. And again, the norm here could be the norm of the kernel classifier, the RKHS norm, the reproducing kernel Hilbert space norm, or it could be a norm based on the neural network weights. Okay. Now here's another situation that we could have. What if we decide to try to label a point that's actually in between two oppositely labeled examples? So I have a blue example and a red example in my original labeled data set. Now I try to introduce the new point U. It'll either get labeled red or blue rather, or red. And in either case, the new interpolation function is going to be much more wiggly and wild than the previous black one. And that's because of the tension between those two oppositely labeled examples. So in both cases, this new point U is going to be difficult to interpolate. It's going to have a large norm of the blue interpolation function and a large norm for the new red interpolation function. So this is what we call our maxi-min sampling criterion. Here's what we're going to do. We're going to look at each unlabeled point or example in our data set. We're going to compute those new interpolation functions and their norms. And then we're going to be as optimistic as possible. We're going to say, well, maybe we'll just get lucky and we'll be able to easily interpolate it as red or blue. And so we'll optimistically choose whichever label makes that norm lower. And then we're going to max over all of the unlabeled examples. And so the idea is to label the point that maximizes the norm of the optimistic new interpolating function. Okay. And the kind of intuition again behind this is that we're going to try to attack the most challenging examples, those that are going to be most difficult to interpolate first, in the hopes that that might eliminate the need to label other easier examples later. So let me kind of talk about a little bit about the properties that we have, mathematical properties of this. Again, we could be looking at a kernel machine in a reproducing kernel Hilbert space, or a neural network. A single hidden layer neural network is specifically what we're focusing on here. And what we can show is that the minimum norm labeling, in other words, the choice of whether the new red or blue interpolation function has a smaller norm, is usually, and by that I mean in most cases, we can prove that it's given by the sign of the current interpolator. So somehow this minimization step is pretty easy to figure out. You can just predict it by the label that's predicted by the current black interpolator that we had before. The other thing we can show is that this criterion, this maximum criterion, selects samples near the current decision boundary and closest to oppositely labeled examples. And I'll show some illustrations of this in a minute, but what that turns out to yield is essentially it reduces to optimal binary search or bisection behavior in one and multiple dimensions. And I'll show that in the next couple of slides. So here's Maximin Active Learner performs bisection or binary search. And what I'm depicting here on the right is a target function, which is a piecewise constant function. It's either +1 or -1, and it has these change points or classification decision boundaries that I'm showing you here, 3 of them in this case. And if we run this Maximin data selection criteria, here's what it does. It basically quickly localizes one threshold, then another in some order, depending on the initial random samples that you take. And so it's quickly homing in on where those decision boundaries are, and we can actually prove a nice little theorem about this. If we have capital N points uniformly distributed on the unit interval and labeled according to a piecewise binary function like the one I'm showing you here with k pieces, then if we're using a Laplace kernel machine or a rectified linear unit neural network, Minimac or the Maximin active learning algorithm perfectly predicts all of the labeled examples after just collecting order k log n examples. So basically, the sample complexity is proportional to the number of decision boundaries in this example. It kind of naturally generalizes what we saw with binary search. So how do you go about kind of showing something like this actually happens? Well, it turns out that proving these results hinges on representer theorem. So in the case of kernels, We use the reproducing kernel Hilbert space representers theorem to show that the optimal interpolator is a superposition of kernel representers, as sort of a standard known result. Then you can go in and inspect the exact structure of the kernel Gram matrix and see that it has block diagonal form. And that form allows us to actually show that the increase of, when you add a new point, the increase in the RKHS norm of the interpolator is maximal at the midpoint between the closest oppositely labeled points. And that's what drives that sampling towards finding those decision boundaries very quickly. In the neural network case, we're using a neural network representer theorem. This is something that I'm going to spend a little bit of time on later in the talk because it's a new result that I think is pretty cool. And we use that to show that the optimal neural network in this case is equivalent to a classic linear spline. And the neural network weight norm then, in that case, corresponds to total variation norm of the second derivative of the interpolator. And that total variation norm increases the most when a new example is, again, added exactly at the midpoint between closest oppositely labeled points. So we have two kind of different approaches based on whether we're talking about kernels or neural networks, both based on representer theorems and both ending up with the same conclusion that this maximum criterion selects points in between the closest oppositely labeled examples. So let me show a little bit about how this looks in multiple dimensions. So here I'm showing a two-dimensional example where we have 4 labeled data points. This is the kernel case, and this is the neural network case here. And this kind of heat map on the right in each case is showing brighter means larger value of this maximum selection criterion. So you see in both cases, this maximum criterion is looking for examples in between the two closest oppositely labeled. So these are oppositely labeled, but further apart. The criterion prefers to try to deal with these guys because it's more certain that there must be a decision boundary somewhere in here. So it sort of naturally has this effect. And here is a little video of what happens in multiple dimensions. So first of all, the sampling basically finds a location of the decision boundary. Then it effectively tracks it along. So in this case, we have 2 regions, +1 and -1, separated by this sort of sinusoidal-like decision boundary. And this maximum sampling is automatically sort of finds that decision boundary and then tracks it, quickly identifying that decision boundary. So it kind of has this flavor of binary search in multiple dimensions. And here's a real data experiment, again, looking at MNIST, the handwritten digit data set. And what I'm showing is training and test error for random or passive learning, that's in blue, and then maximin in red and orange. And this database maximin is just a variant of maximin that's a little bit more sensitive to the data distribution, and that can improve the performance of the maximin criterion in active learning at earlier stages in the learning process. But the takeaway message here is that this test error improvement is pretty large again, a 3x to 4x improvement in terms of 3 to 4 times fewer samples needed to learn a good classifier using this active learning approach relative to standard passive learning. Okay, good. So now I want to kind of spend the rest of the talk. How am I doing here? Yeah, I'm doing pretty good. So I want to talk about this idea of the function norms and the maximum criterion. The choice of the function norm is pretty important. Obviously, if I choose a different norm, I'm measuring regularity or smoothness in a different way. So what's the right norm to use? In the case of kernels, it's pretty natural. We'll just use the associated reproducing kernel Hilbert space norm. In the case of neural networks, what I suggested is that the weight norm is something we can use, like the L2 norm of all the weights in the neural network. So why is that a good choice? That's what I'm going to spend the rest of the talk on. So to do that, we're going to talk about representer theorems. And so I just want to remind everybody what a representer theorem tells us is that solutions to certain infinite dimensional function space learning problems, so learning from data in infinite function spaces, can be represented in terms of finite dimensional parametric functions. So the solutions to these problems cast in infinite dimensional function space actually have finite dimensional parametric solutions. So this idea originates, the first instance of a representer theorem is in the famous work from Kimmeldorf and Waba, Grace Waba, another super famous and wonderful data scientist from University of Wisconsin. So you can see we have a great legacy here at Madison. So she introduced this idea of representer theorems, and since then it's obviously been a huge impact on machine learning and statistics and everything. So here, of course, we have kernel machines which generalize this idea of representer theorems to all sorts of reproducing kernel Hilbert spaces. That's been an active area of research since the 90s. More recently, people have been looking at representer theorems in Banach spaces. This includes work on generalized splines, reproducing kernel Banach spaces, total variation regularization, and atomic representations. And the neural network representer theorem that I'll talk about is an example of these Banach space results. So here's the classical RKHS representer theorem. It says that if you have a reproducing kernel Hilbert space with some kernel K, then for any training set and any loss function and any solution to this regularized empirical risk problem, where the regularization is in terms of the RKHS norm, then those solutions have a representation in the form of just a linear superposition of kernel functions. Each kernel function is evaluated at one of the data points, and there are just real valued coefficients out in front. So we have this very, very simple finite dimensional representation of solutions to this infinite dimensional function space optimization problem. So it's kind of remarkable. Now it's so routine that we don't even marvel at it as much as we probably should. But it's kind of an amazing result and super cool and obviously super useful. So I have a student, Rahul, he's a super smart guy, and he posed this great question. He said, is there a representer theorem for neural networks? And it turns out the answer is yes, but not in a Hilbert space. So here's the informal statement of Rahul's theorem. It says that there's a non-parametric Banach space F equipped with a norm such that for any training set and any convex and coercive loss function L, there exists a solution to this regularized empirical risk problem, where again, now the regularizers in terms of the Banach space norm, that has a solution that can be represented as a finite width single hidden layer neural network. So the number of neurons here is less than or equal to the number of data points in the training set. And these are the neurons, and I'll explain more about the actual form of this neural network. But it's kind of a really interesting result because it's saying that we're casting this problem in an infinite dimensional Banach space, but the solutions are finite dimensional neural networks. So I'm going to spend some time explaining this because it's not exactly trivial or super easy to understand. So I'm going to go through it in steps. So try to hang with me here. So first of all, what is this neural network Banach space involved in that theorem? Well, it's actually a family of Banach spaces indexed by integers. So each of these Banach spaces, f sub m, is a set of multivariate functions. And these multivariate functions are smooth in the Radon transform domain. So what we have here is the function, the Laplacian, which is a differentiation operation, followed by the Radon transform. And then we're looking at smoothness measured in the L1 sense in that Radon domain. So I'll explain why we have the Radon transform and everything in there. Smoothness being measured by taking derivatives is very natural and standard. Why we look in the Radon domain is a little not so obvious, and I'll explain that as we go. But first of all, I just want to tell you what the result basically says. It says then that neural networks of this form are the solutions to fitting data and minimizing this Banach space norm that I just told you about above. The neural networks themselves, here's just a little bit more specification about what's going on here. It has weights. The V's and W's are just real valued weights. The C function here is just a simple kind of generalized bias term. It turns out to be a polynomial function, so that's just a simple polynomial. The B's are biases, of course, and then the activation functions here, these are truncated power functions. So in the case of m equals 1, this truncated power function is just the familiar rectified linear unit that is used all over the place. For larger values of m, you get like rectified cubic, rectified quintic, so higher order polynomials that all have this activation at 0. Okay? So that's what the solutions to these optimizations are. The atoms are effectively these neurons with these truncated power function activations. So how does this relate back to the weights of the neural network? That's kind of important because, as I said before, in our active learning algorithm, we're using weight norms to guide that maxi-min criterion. And what you can show is that for any neural network, its function space norm is just the neural network path norm. This is a familiar kind of norm that people have proposed before for analyzing neural networks. And so it's just a product of norms of the input and output layer weights. Another kind of cool feature about these F norms is that they control the Rademacher complexity of neural networks. So if we let F hat be the solution to minimizing this empirical risk, subject to a constraint on how large the norm is of this interpolating function, so that bound is B, then we have a generalization bound that says the test error of F hat is less than or equal to the training error of F hat plus a term that's proportional to that bound over the square root of n. And so what this is telling us is that if we can find a neural network that not only has a good training error, but also has a small norm bound, we'll generalize well. So that's kind of a nice connection between these norms and generalization error. So now I want to get back to this question of where does this Radon transform come in? So neurons in a neural network are special examples of a general class of functions known as ridge functions. So I'm going to illustrate a ridge function here for the rectified linear activation function. So what we're going to do is take a fine linear transformation of our input x1, x2. So the filtered Radon transform of the Laplacian of a ReLU activation ridge is just an impulse in the Radon domain. And the location of that impulse indicates the angular orientation and the offset or bias of that neuron. Okay? So here's the kind of general story then for single layer hidden neural networks. The differentiation operation of the Laplacian is annihilating the linear or polynomial surfaces associated with those ridge functions, leaving only the linear boundaries of the activation thresholds. And then the Radon transform is effectively extracting the orientations and offsets of each neuron, producing impulses in the Radon domain. And then finally, this norm is measuring what you could think of as sparsity in the Radon domain. So here's a picture of this for a 7-neuron network with rectified cubic units. So the function itself is a piecewise cubic function. This is what it looks like. Top-down shown here, and superimposed over that top-down picture is the Laplacian applied twice to that piecewise cubic function. What you're left with are just these lines, and these lines are indicating where different neurons turn on and off, the activation thresholds. And then if we take the Radon transform of that result, of the Laplacian, we get a representation in the Radon domain where we just have an impulse located at the orientation and offset of each neuron. So that's what that's kind of where that all comes together. And how do we actually end up proving this representer theorem then? Well, first of all, you have to look at the properties of this overall composite operator, which is the Laplacian followed by the Radon transform. And one important feature of this is that the green functions of these operators are truncated power ridge functions, the ones I was showing you before. And the null space are low-degree polynomials. And so what this means is that every function in one of these Banach spaces can be represented in terms of a finite measure. So if we apply that operator to a function, we get the measure, and we can use the measure to represent the function by computing or forming the pseudo-inverse of that operator, applying that to the measure, and then adding an appropriate polynomial, which is a thing that's in the null space of this operator. Then minimizing this L1 norm of the operator applied to F is equivalent to minimizing the total variation in the sense of measures of this measure mu. That minimizing total variation of a measure subject to linear constraints. The linear constraints are just coming from our data. That's a classic measure recovery problem, and it's known that the superposition of Dirac's is a solution to it. And so then if we take that superposition of Dirac's, apply the pseudo-inverse operator to the solution, we get a superposition of ridge functions, which is exactly a single hidden layer neural network. So those are sort of the ingredients that go into proving that representative theorem. So almost finished here. What are the takeaway messages? So first of all, nonparametric learning problems with this F-norm regularization have atomic solutions. The atoms are neurons, and the overall solutions are finite width neural networks with truncated power activations. The F-norm controls the Rademacher complexity, hence the generalization error of those neural networks, and adding a training example increases the norm and requires adding an additional neuron, and that's sort of the key heuristic that we used in our active learning algorithm. A couple of things that I didn't have time to talk about. First of all, this F-norm regularization is equivalent to certain forms of weight decay in stochastic gradient descent training of neural networks. And so it's very easy to implement this in practice. And another cool fact is that if you reduce this to the one-dimensional setting, you get back to classic polynomial splines. So these are just classical polynomial splines in 1D. And so I'm just going to finish by illustrating those last 2 points with a little example. So this is an example where we have 6 data points, and I've interpolated them with a cubic spline. So that's what the cubic spline interpolation looks like. Here is the interpolation result using a rectified cubic unit neural network trained with SGD using weight decay. And you can see, as our theory predicts, it should be exactly that cubic spline. That's what we get. On the other hand, if we take the same neural network, train it with SGD, but no weight decay, then we can get other strange solutions. For example, this one, which has sort of an extra unnecessary bump in it. So it's not as regular, not as smooth. And so it is really important that you use this kind of regularization to get sort of the nicest functions that will generalize as well as possible. So here is just my conclusions, and then I'm happy to take questions. I kind of reviewed a little bit about theory methods for active learning. Those are kind of well-developed in classical statistical learning theory frameworks like VC theory, but that classical theory really isn't adequate for understanding modern machine learning systems like neural networks. I propose this new framework for active learning based on these maximin criterion and minimum norm solutions in appropriate function spaces. And we have some theory and some nice experimental results to support that. And I think, though, there's still tons of opportunities because, of course, everything I told you about was just for single hidden layer neural networks. What can we say about deep neural networks? Can we use similar ideas there? It would really hinge on finding appropriate norms for those neural networks and also computationally efficient algorithms for carrying out those active learning algorithms. And so here are just a couple of references to the 2 main papers, and I'll just say thanks and happy to take questions.
Okay, yes, thank you so much, Professor Nowak. So the first question is regarding the first paper you discussed. It comes from Kwang-Sung, and the question is, what is your thoughts when the labels are moderately noisy? For example, in MNIST data, if you are at label noise, then the interpolator does not perform well, and in that case, adding a regularizer actually helps, assuming you don't tune the kernel parameters separately.
Yeah, I mean, that's a great question. Of course, we could, I sort of showed everything when I depicted in terms of actual interpolating those points. If I used a different loss function like hinge loss or something like that, we wouldn't necessarily be running our interpolating function through the points exactly. We'd just be getting them to have a good margin on all the training data points. And, I guess the same question comes up just in normal passive learning. What happens when I drive the training error to 0 and there's label noise? Sometimes, some theory and experiments show that you can do that and you don't really suffer too much, even if there is label noise. And so it's an important question, and it's not exclusive to the active learning paradigm. It comes up in passive learning too. So my thinking is using appropriate loss functions, you might just as well, again, fit to the training data. In other words, drive that loss to 0, even if you think there might be label noise. Sometimes you can still get good generalization out of that, just like we can in the passive case. Other ways to deal with it would be to explicitly try to account for label noise in the active learning process. That's something you can do, but of course, doing that appropriately would probably require some additional knowledge, or you'd have to come up with a way of adapting to the level of label noise. And those things have been looked at, but of course, it gets very tricky in this nonparametric setting.
Okay, thank you. So another question is, so in the first paper, you talk about the exponential speedup. I was wondering whether this exponential speedup leads to a regret bounds in some sense, whether it's a log t regret or a sublinear regret.
Yeah, so those exponential speedups are sort of associated with localizing the decision boundary in the binary search example, for example, that I showed. But what, if I maybe just go back to that slide, let me just get out of here and go back to it. Where was that? Yeah, here. So what these exponential speedups are in terms of the so-called excess risk, the difference between the error rate of your learning classifier and the Bayes error rate. And so I'm not sure if that answers the question, but the way that these speedups are happening is just basically how quickly is your learned model approaching the Bayes error rate.
Mm-hmm. Okay, thank you. So another question is, is that what is the property? Which property of the ReLU function or Laplacian kernel do you need for the theorem, for the representative theorem? And what about other activation functions and kernels? Can you say something about that?
Yeah. So first of all, let me say something about other kernels. So in that binary search result, we did use some special properties of the Laplace kernel, which is just the double-sided exponential. And that was sort of important there. If we use other kernels like Gaussian kernels or whatever ones you want to choose, we see similar behavior, but not exactly this perfect bisection. That's sort of a special property associated with the Laplace kernel. But we can say some things about other kernel methods. And in our paper, we go through what happens with other kernels, what can you say about them, and so forth. In terms of neural networks, of course, you could use other activation functions, and you could say my way of measuring the norm of a neural network function is the neural network weights. But the problem is there, it's not really clear how that neural network weight norm relates to the overall function that the neural network is representing. And so one of the nice things about the representer theorem that we have is it makes that clear connection between the neural network weights and the function space norm. That representer theorem is very particular in terms of what the activation functions are. They really do have to be these sort of rectified polynomial activations, which the ReLU is one special case of. So generalizing those type of representer theorems to other activation problems, or activation functions rather, is an open problem. And I don't know exactly how straightforward or easy it is. I mean, there's a lot of things going on in those examples, in the proofs of those cases that make it unclear exactly how easy it would be to come up with representative theorems for other activations.
Mm-hmm. Thank you. So another question is regarding the model misspecification and the inductive bias you mentioned. So the question is, what about we have multiple types of models running simultaneously, and then we apply a active learning method to learn the model or to learn how to aggregate those estimators at the topper layer.
Yeah, so that's an interesting approach, right? The idea of using multiple models, because you really don't know which model will be most appropriate for your problem at hand. So of course, if I have training data, I can fit each model to the training data, and then I could try to select which model is best based on those training data, maybe through some sort of bandit type optimization, or I could take a weighted combination in some appropriate way as was suggested. But how to combine all that with active learning is not as clear, right? Because again, the normal active learning approach uses the form of the model. Say we're looking at linear classifiers versus decision trees, and you want to use those two in parallel. Well, a decision tree might be encouraging you to ask for a label for an example in one part of the data space, and the linear class server might prefer you to take a sample from another part of the data space. So how do you decide which model to follow in choosing that example? Can you somehow do another layer of optimization over that? That's a super interesting question. And I don't know of any great answers off the top of my head, but certainly would be something that would be interesting to look into, I think.
Okay, thank you. So another question is regarding the first part of your paper. You mentioned you introduced the max-min approach for taking actions. I was wondering whether there's any connection between this method and the UCB, the Gaussian UCB method, where they have add a bonus to take action, to drive the decision making. Whether this has any connection with the optimism in the face of uncertainty principle.
Yeah, I mean, I don't know of any formal connection between the methods. I mean, they share some similarities, and there may be some ways to work out connections, especially with Gaussian process models and Gaussian kernel methods and those sorts of things, but it's something that we haven't looked at all. So as far as I know, the connection is just sort of superficial at this point, but maybe there's something deeper going on there. That's another really interesting question.
Okay, thank you. And the last question is that, is it possible to extend those classification results to the regression setting?
Yeah, I think so. That's something that Mina and I have talked a little bit about. We haven't really developed anything too far yet, but I think it's a really interesting question, and I do think there would be some things that you could do in that direction. We have some initial ideas, but we, like I said, really haven't developed it very far yet. I'll mention that there is some work that goes back a ways to something I did with Rebecca Willett and Rui Castro, where we looked at active learning and regression in a particular way that had shared some features of what we discussed here, namely this idea of focusing on areas where there's a sharp transition or a change point or a lot of variation in the function. And so that, I think that paper is called Faster Rates in Regression Through Active Learning. So that might be something, if that person wanted to take a look at it or follow up with me, I could send a pointer. But yeah, I think that's an important direction to explore, and certainly something we're interested in.
Okay, thank you so much. So I guess we are running out of time, maybe. Thank you again for the very nice talk. And we have almost 1,000 audience across all the platforms.
Super. Yeah. Well, that's fantastic. Thank you all for organizing. Thanks to everybody for tuning in. And if people have further questions, they can feel free to shoot me an email. So I appreciate the opportunity to talk to everybody today. It's fun. Thank you.
Thank you so much.
Okay. I'll sign off. Bye, everybody.